right? The simplest equation of, I shouldn't say it's the simplest, it's not the simplest, but one of the most important equations, this is just an example, is that the delta x, the change in position of something, how far something moves, that's all this is v naught times t plus 1/2 times a times t squared. Now, at this point, you say, whoa, 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 he's writing a bunch of math on the board. I don't understand it. All right, first thing you got to do when you start to learn physics is you have to take a deep breath. You have to say, none of us were born with this knowledge. Nobody came out of the womb and said, oh, I understand motion. I understand equation. Nobody did. The first time I looked at this equation many years ago, I scratched my head. I was like, what does it mean? Okay, and when you learn more and more and more, it becomes like a language where you can start to not just look at the symbols and be confused, but you start to read words. You know, when you read a book, you don't sound out the words, you read the whole word. But when you were 3 or 4 years old, you had to sound out the words. So if you see an equation that I write on the board here or in your textbook or on anything in life, if your first reaction is, whoa, whoa, I don't get it at all, you got to take a deep breath. Okay, and you got to just kind of work through that because none of us understand it in the beginning. So let's pick apart this one little equation and we're going to learn something from it. All right, this is what we learn in the very, very, very beginning of physics, and we're going to work our way through magnetism and electricity and thermodynamics and optics, and we're going to talk about all of it in this one lesson. All this is, this little delta symbol, this triangle means change. It literally means change in x. X is the position of something, anything. It could be a rock. The change in position, how far it moved. Or another way you can say it is distance moved. So how far something moves is equal to what? All this junk over here. And all of this stuff, this sub-zero, v, we call it v naught, v sub-zero, this means the velocity something had. We're going to talk a lot more about velocity and speed and distance later. We're just getting an overview now. But I think you all understand velocity. That's how fast you're going down the road, right? V naught means initial velocity, right? At time 0, that's why it's got a little 0 there. At time 0, what speed did you have? Well, this is going to be initial velocity multiplied by the time, and that gives you the distance traveled due to the initial velocity. Now, I want you to ignore the rest of the equation. Just ignore it for a second. What are the units of velocity? The units of velocity are meters per second. So that's a unit of meter per second. We're multiplying by time, which is seconds. So remember from fractions in algebra, when you have 1/2 and then times 2, you have a same thing on the top and the bottom. The 2's will cancel. Well, here you have the same thing with units. That's one of the most powerful things we learn in all of science is how the units work. So you have a seconds on the bottom and the seconds on the top. They cancel. And what you get here is a unit of meters. So when you move, 5 meters per second over 10 seconds, it makes sense. Every second you go 5 more meters, 5 more meters, 5 more meters, 5 more. So if you multiply by the number of seconds, this term, see, we're reading the words now. The individual letters are here. We're reading the words. This term tells me how far I moved because my initial speed was this, and I traveled for this long. And this is how far I moved due to this term. All right. Now this term is the distance due to the acceleration. Because we're saying here that we have an A. A is acceleration. This is also the time. So we have two things going on here. We have some initial velocity that the thing is moving at. But then the acceleration means we're either speeding up or we're slowing down. So maybe I have a rocket thruster on the back and I accelerate this thing. And we're going to talk a lot about acceleration, but acceleration means you speed up, right? So this term, I could go through the units. I'll do it and when we get to the lesson on this. This term is the acceleration times the time squared times a 1/2. Now, why do we have a 1/2 there? Why do we have time squared there? We're going to talk about all of those in their lessons. The only reason I'm putting this on the board is to show you the anatomy of an equation. The distance you travel is equal to the distance traveled because of your initial speed times the time, plus some additional distance you travel because you're accelerating. You're speeding up. And that's above and beyond the initial speed you had. Of course, time is involved here too. So you have this distance plus this distance, and that's a total distance you traveled. Now, why did I really and truly write this on the board? Right? Remember back from algebra? You know, when people complain, why do I learn this? Why do I learn this? Remember we talked about y is equal to x squared. Now I could write a more complicated equation. I could say y is equal to 2x squared plus 3x, minus 2. I could write some variation of it, but generally this is the basic parabola that you learn how to graph. It kind of has a smiley face shape to it in algebra, and then we learn more complicated forms of it, okay? So the reason that we learn those things in algebra, you can see the similarity. Notice you have y is equal to x squared. Here we're not calling it y, we're calling it x. We have an extra term here, but we have t squared, x squared. So in physics, we often talk about how things change with time. And so when we're talking about motion, it's how does it change with time? So the variable of interest is time. But this equation, you can see it's something is calculated based on, you have a t there, and then you have a t squared here. Look in this equation. You have an x and you have an x squared. The form of this equation, the big picture form of it, is basically the same as this one. I mean, if you want to make it exactly the same, I'll just take the 2 off. This is something you learn how to graph in algebra. It's some number times x squared plus 3 times some variable x. So here we have 1/2 at squared. This is just a number times t squared and then a number times t. We learn in algebra how to handle these equations and graph them and understand what a parabola is and what does it look like and all that because it pops up in physics. It describes motion. This is one of the equations we're going to spend a lot of time solving problems. And the biggest question I get is, why do we learn this stuff in math? Well, here's why. Because we take that and we use it in like the very first chapter of physics. All right? So I already talked about the idea that in this equation for motion here, x is what we call the position. This is basically where the thing is going to be. And then we have v in here. In this case, it was the initial velocity. We called it velocity. Right? And in this equation, this is why I picked this equation, we also have a, the acceleration. The acceleration. Right? Now here's where we pull in a little bit of calculus into it. Calculus is all about, at least the first part of it, it's all about how things change. And when you talk about how something changes, you really need to compare it, change compared to what? In physics, a lot of time we're talking about how something is changing with respect to time. Is the temperature in this room increasing with respect to time? In other words, as time goes on? Or is it decreasing as time goes on? All right? In this case, we're talking about how does position change with respect to time and so on. If you look at how the position of something changes, we'll call it change. This triangle means change with respect to time. Then you get something called velocity. I want to say that one more time. If you look at how something changes in position with respect to time, you get velocity. What are the units of velocity? Meters per second, or miles per hour, or kilometers per hour. It's a distance divided by a time. How does something change over what time period? So when we say something changes in position with respect to time, what we're doing is we're calculating its velocity because velocity units are distance over time. So when we take and look at how something changes in position with respect to time, what we get is something called velocity. Now, if we take the velocity and we look at how does this thing change with respect to time, how does the velocity change with respect to time? We get a new thing, which we call acceleration. You're driving down the road, you're going, 10 kilometers per hour, and then you hit the gas, or you hit the accelerator, and you speed up, you're pushed into your chair. You have increased your velocity. You're changing your velocity with respect to time because the change in velocity happened over 1 second or 2 seconds. So this is a very important thing. How the position changes with respect to time, we call it velocity, meters per second. How the velocity changes with respect to time, we call it acceleration. These are all interrelated into each other. And so in the language of calculus, what we say is that the velocity is equal to the derivative of the position with respect to time. This thing is a calculus thing. You learn it in calculus. This is not a calculus class, but we are going to use this a lot in the application of physics. What we're saying is the velocity is, the d means the change in x with respect to the change in time. How does x change with respect to time? It's exactly what I wrote in words. And The acceleration of an object, what can you guess what it would be? It's how the velocity changes, dv, with respect to t. How does the velocity change with respect to time? Both of these things are calculus. Now you can get away with doing this without using these things called derivatives if things are changing not so crazy, right? But if things are speeding up and slowing down, speeding up, and everything is all jagged and moving around, you have to use calculus because there's no other way to do it. So in an algebra-based physics class, then everything would be constant and smooth and not changing, in a way that you require calculus. But in the real world, with a rocket, in a rocket engine that kicks you and it changes and everything's changing, and then you have to use calculus. So then we're going to be using the language of calculus here. This is called the derivative. The velocity is called the derivative of the position. The acceleration is called the derivative of the velocity, of course, with respect to time. And these equations of motions can be used to calculate where things will be in the future. So far, we've talked only about how, this one little equation, where things are going to be in the future. The position of something in the future is equal to this term plus this term. This is the distance traveled, and the distance traveled, you add it together, you get a new distance traveled. But this is just in one dimension. This is like if you were an ant and you can only go up and down a wire, like you're living on a wire and you can only go that way or that way. The x position is the only thing you have in your universe. But in a real world, we have x and we have y, and then we also have z, right, up and down. So we have 3 dimensions of space. So when we get past the initial equations, we want to talk about what we call we want to talk about how things, instead of in the x direction, we want to talk about how things fall in the y direction. So the nice thing about this, notice there's an acceleration here, a. And what we do, if we turn this thing on its side and we talk about how things fall, what we do is we just say that this acceleration, we just rename it minus g. And this is the acceleration due to gravity. And it's 9.8 meters per second squared on Earth. Now we're going to talk about the units of acceleration later. This is just an introductory class, but what we're saying is when things accelerate, in the x direction, you have to be giving it the gas or something. But if you drop something, it accelerates because it's speeding up. It's starting from 0 and it increases its velocity all the time. And it's oriented downward 9.8 meters per second squared. That just means it picks up speed 9.8 meters per second every second. Every second that goes by, it increases its velocity 9.8 more meters per second. 9.8 more meters per second. But the nice thing about this is what we can do is we can go back up to this equation, the equation for x. We can rewrite it in terms of y, and instead of x, we're going to call it the y direction, the up and around, the falling direction. We can call it delta y. And then we can do the same thing here, v naught times t. But notice it's plus 1/2 at squared. But now a is just the acceleration of gravity, which is a negative number, negative g. So we can put minus 1/2 gt squared. Notice that this equation is of exactly the same form as the one we started with. V naught t plus 1/2 at squared. The only thing we did is we put a negative g for the acceleration because gravity always acts downward. Upward is positive y, downward is negative y. So we put a negative g in there. So we spend quite a bit of time learning how things fall. And when they fall, they accelerate. They don't just go at a constant speed, they accelerate, okay? So we use this equation along with others that we'll talk about to calculate where something will be, how far it will fall. And that's going to be equal to its distance because of its initial velocity. Maybe you throw it down, for instance, and then you're going to be adding more distance traveled because it's accelerating downward at g. And this time means every time that goes down, or every second that ticks by, you're squaring it, you're multiplying, and then this distance is added to the distance there. So we use that equation. And the next thing we do after we get those equations under our belt is we talk about projectile motion. And after we work on projectile motion, we talk about forces, which we're going to get to very soon, and energy. Forces and energy, and then we're going to go on past there. So projectile motion is a simple case of playing in a park. So here you have some person standing right here, and I have a ball, a little soccer ball, and I kick it at some velocity like this. And then initial velocity, notice I put a naught there because this is the initial velocity. I call it 10 meters per second. But look what I have here. The ground is basically, right here. and I kick it at some angle. And this angle, I don't know, it could be anything, but let's call it 34 degrees or something, right? Now what's going to happen from experience, you know, is that you're going to kick this thing at a angle like this, and it's going to go up and it's going to fall back and hit the ground. So what's going to happen is when you kick this thing up, it's going to go up, it's going to reach some maximum height, and then it's going to come down and hit the ground like this. This is called projectile motion. Now, what do we want to do with something like this? What do we want to calculate? We want to calculate things like how high did it go in its maximum height. We want to calculate things about like how far did it travel downrange. We also might want to calculate how many seconds did it remain in the air. What was its hang time, right? So we have various modifications of this. You know, maybe it's a cannon, maybe it's a rifle, maybe it's a spacecraft, but whatever. Notice that in this case, there's two dimensions of motion, x and y, and so this is the y direction and this is the x direction. Now let me tell you the secret to how we handle this. What we do is we apply one of the most powerful ideas in all of physics, and that is when you have something called a vector quantity. We're going to talk about vectors in just a second, but velocity is a vector, right? When you have a vector quantity, what you can do is you can split that motion up, the angle motion, the 34-degree motion. You split it up into a motion along the x direction, and you also split it up into a motion purely in the y direction, and you treat them separately. That is so fundamental, I'm going to repeat it again. When we have a vector quantity like velocity is that it has some magnitude, some size, and also it has some direction to it, okay? And we can split it into a horizontal motion that's just purely going on the x direction, and then we can also split it into a vertical motion. Of course, the vertical motion means it's going to come up at a maximum, and then it's going to come right back down. The horizontal motion is it's just moving this way like this. If you combine the up and down motion with the horizontal motion, it traces out this path. But instead of trying to deal with that curved, ugly path, what we do is we write equations in the x direction, and we have those equations, and we have separate equations only in the y direction, and then we solve them separately. So we can break problems up into simpler forms. I already gave you an example of this. This is an equation in the x direction. This describes the motion in the x direction only. Its initial velocity in the x direction, its acceleration in the x direction, and you have time, and then you can calculate where it's going to be. But when we came to the y direction, notice it was the same equation. We just replaced the acceleration with g because we know what g is on Earth, right? But its y position is equal to its initial velocity in the y direction and its acceleration in the y direction, and we have time there as well. So I already gave you an example of splitting up these equations in the x and y direction. Now, we're able to do this here by treating the x motion and the y motion separate because the velocity is what we call a vector quantity. So let me just go over here. Let me go over here. I will write down some examples of vectors, right? Which are very, very, very important, right? So what are some examples of vectors? Well, velocity. Why? Because it has a strength 10 meters per second and it has a direction 34 degrees. This vector is different than if I was going 10 meters per second at this angle. That's a different vector because its direction is different. If it was angled down into the ground, maybe I kicked the ball down toward the ground, still 10 meters per second. If I angle it differently, it's a different vector because the direction is half of the vector quantity. The speed, the 10 meters per second, is important, but the direction is equally important because you get a different answer for this if you angle it differently, right? What are some other vectors? The acceleration. If I'm speeding up or if I'm slowing down, those are different vectors. The acceleration has a vector quantity, is a vector quantity as well, right? What about force? Now we're going to talk about forces later, but when I push on something, that's a vector. Why? Because it's how strong I'm pushing, but it's also what direction am I pushing. If I have this marker here, if I push like this, or if I push like this, or if I push like this, those are all different. Even if it's the same amount of pushing, the direction is different. It's a magnitude and a direction. Now let's get a little bit crazy here. What other vectors do we have? Well, there's something called an electric field vector. And there's something called a B field, a magnetic field vector. We're going to learn about these much later, but at the end of this lesson, we are going to write down what we call Maxwell's equations, which talk about the E field and the B field. So an invisible field in front of you exists. You can't see it, Well, actually, you sort of can because the light is hitting your eyes and light is made of these fields, right? The photons of light are made of these fields, right? But let's just put that aside for a second. You can't see the magnetic field in front of you. But surrounding this thing that we call a magnet, this is called a magnet because I can put it on the board, right? And it sticks there. We all know what magnets are. Surrounding this thing is an invisible field of vectors called a magnetic field. They have direction, they point in a certain direction, and they also have a strength. They're vector quantities, right? And then we also have electric fields that surround electrons and protons as well. So we have electric fields and we have magnetic fields. You put them together and they dance in a very beautiful way, which we call electromagnetic waves. They wave and they carry light to your eyes. They carry microwaves. They carry radio waves. They carry gamma rays. All of those things are different types of electromagnetic radiation. So when you have any of these things, velocities, accelerations, forces, electric fields, magnetic fields, I can go on and on and on. Those are vectors. That means you can treat the analysis by splitting the vector into an x direction vector and a y direction vector. Let's pretend I had some magnetic field pointed like this at an angle. Well, instead of dealing with that, that's ugly, that's nasty. Let's just treat it as an x component pointing this way and a y component pointing up, the sum of which makes the angled vector that I had to begin with. It's always going to be easier to split your problem into an x direction and a y direction. Now you might say, okay, here are these vectors. I gave you a lot of examples of vectors. What's not a vector? It seems like everything is a vector. So what is not a vector? Well, lots of things are not vectors. What about the temperature in this room? The temperature in this room at every point in space is an invisible number. If you could see it, every number in front of us would have a little temperature bubble, which would tell me the number. Maybe this is like, 89 degrees Fahrenheit or whatever. Or if we talk about Kelvin, it could be, 280 Kelvin or whatever. And the different numbers at every point, but there's no direction for a temperature. It's just a number. That is called a scalar. So when we have something called a scalar, it has a size but no direction. So temperature. Another great example is pressure. If I go deep underwater and I dive, I feel the pressure on my ears. But there's no real direction associated with pressure. The pressure at all the points down there, it just is what it is. It doesn't point this way and that way and backwards and forth. It's just, it's a pressure, it's just a number. Temperature, pressure. There's many other examples of scalars. But the most interesting things in life are vectors. The magnetic fields, the electric fields, the forces. Those are things we're going to be talking about for a long time. And while I have you on the subject of electric and magnetic fields, I want to share with you one of the most mind-blowing things that I've ever learned in my whole life, okay? And that is, we live on Earth and we're stuck to the ground by gravity, right? So we kind of think gravity is really strong. But actually, gravity is really, really weak. It's really, 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 really weak compared to the other forces of nature. So this is a magnet, right? And then we have the magnetic forces and we have the electric forces, right? So we know that opposites attract from, when we have a positive and a negative charge, they attract, and like charges repel. We learn this kind of thing later on. It also gets into chemistry as well, right? So it turns out that the electric force, the force between two charged particles, is much, 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 much stronger than gravity. And that's something we don't think about, but it actually is. And so when we get into chemistry and things, that force dominates everything that happens, right? So you might say, how much stronger are we talking about here? Well, if you remember back to math class, right? 10 to the power of 2 is 100, right? Because that's 10 times 10, right? So if it were, if I'm telling you the electric force is stronger than the magnetic force, would it be 100 times stronger? No, it's much stronger than that. What about 10 to the power of 3? What does that look like? That's 1,000. That's 1,000 times bigger. Is the electric force 1,000 times stronger than gravity? No. It's much stronger than that. What about 10 to the power of 6? That's 10 times 10 times 10 times 10 times 10 times 10, right? And that works out to 1 million. All right, is the electric force 1 million times stronger? No. It's much, much, much stronger than that. You see where I'm going with this. What about 10 to the power of 9? Right, that works out to be 1 billion. Here's another triple zeros, another triple zeros, and another triple zeros. Is the electric force 1 billion times stronger than the gravitational force. No, 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 no. It's much, much stronger than that, right? Let me tell you, finally, how much stronger it is. The electric force is approximately 10 to the power of 39 times stronger than gravity. Let that sink in for a second. You know, 10 to the power of 3 is 1,000. 10 to the power of 6 is 1,000,000. 10 to the power of 9 is 1,000,000,000. No, no, no. The electric force says 10 to the power of 39. Look at how many more zeros you would have to add behind a number 1. And that's how much stronger the electric force. It's incredibly strong. It is so incredibly strong. We don't feel it, though, every day, because all of our atoms in our body, they have protons in the nucleus, which are positive, and electrons orbiting, which are negative, and they balance each other out. So the net force of a neutral atom is 0, because we have an equal number of opposite charges. But when you start talking about physics later down the road, nuclear physics, where you take an electron off by itself, or you take a proton out by itself, and you start having to calculate the forces involved in those tiny little things, they completely dominate gravity. So that's just one thing I wanted to bring up to you, just because it's interesting, and we think gravity is so incredibly strong, but you know, electric forces and magnetic forces are millions and millions and millions. I don't even have a word for it. I'm sure there is a word for it. Millions of times stronger. In fact, you can kind of illustrate that a little bit by just kind of considering the following. So here I have a pen. This is just a ballpoint pen. And right now, if I drop it, the Earth is attracting it. We're going to talk about gravitation in a second. The Earth is pulling it down with a force. But this little magnet here, I can actually attract this pen, and I can lift it up, and I can resist the force of the gravity. In other words, the atoms in this magnet are overcoming all of the forces of attraction of the entire planet pulling on this thing. The whole planet Earth, even something in China, Australia, the bottom of the ocean, all of the atoms of Earth are attempting to pull on this down, and it's succeeding, it's falling down. But this little bitty thing right here, the force of magnetism, is so much stronger than gravity that it can overpower that, if I can get it to orient right, and lift it up. You get the idea. Lift it up. If I can do it right. And lift it up and overcome that guy. Because why? The electric forces and the magnetic forces are millions and millions and millions and millions of times stronger than gravity. All right? So now that we talked about forces, kind of in a roundabout way, now we have to talk about the actual topic in physics of a force. Now, we measure forces in physics in a unit called newtons. This is after Sir Isaac Newton. We're going to get into exactly how big of a newton is, but a newton is something you can hold in your hand pretty easily. Okay, it's not like a large amount of force, but it's not a super small amount of force either. It's something you could resist with your hand pretty well. A force is exactly what you think it is. A force is when you push on something or if you pull on something. But it doesn't have to be with your hands. It could be any force. It could be the electric force, right? That pushes atoms apart, or electrons or whatever. It could be the magnetic force, like pulling on that pin. That's a force. It could be the gravitational force attracting me to the ground, right? Or it could be any other combination. A rocket engine could be pushing with some sort of force. And one of the most famous equations that we use all throughout physics is called F equals ma. Now the force is a vector, so we put a little arrow on there. And the acceleration is a vector, so we put a little arrow on there. And if you don't believe me, look at our table. Force is a vector and acceleration is a vector. So we put them with little arrows on top. And that just reminds us that the force is not just a number, it's a number with a direction. And the acceleration is not just a number, it's a number with a direction. The direction is equal parts to what a force is, or an acceleration, or a velocity. It's equal in importance. It can't tell you how important that idea is. It's going to come up again later. So what this equation says, force equals mass, the mass of an object. So this is the mass. We haven't really talked about mass yet. So this is mass in a unit which we call kilograms. A kilogram is also something you can hold in your hand pretty easily, right? Now, this force is equal to whatever the mass of the object is times the acceleration. What this basically means is that if I apply a force, then I cause an acceleration. Or another way of thinking about it is, if you observe something that has some acceleration to it, there must be a force involved. Because the force on an object is exactly equal to the mass of the object times how it's accelerating. So another way of looking at it is, there's, these equations look so simple, but you cogitate on them for years and years, and you realize how important and profound they are. What it means is that since these are vectors, they're also lined up in the same direction. Some force in a direction is going to be exactly equal to the mass times some acceleration that happens in a direction. So another way of kind of writing in words what this equation actually means is that forces cause acceleration. They cause acceleration. I'm going to underline this. I'm going to box it. I'm going to put little smiley face sun around it. They cause acceleration. If you have no forces, then you have no acceleration. And that means nothing's acceleration is when you increase speed or decrease speed. Let's take the opposite situation. Let's say you have no force, 0. Then therefore, to make this equation equal, then the acceleration has to be 0 too, because remember, mass is always a number, it's positive. So if your force is 0, then if you solve for acceleration, you have to have a 0 acceleration also. If you have a positive force, then you must have a positive acceleration. If you have a negative force acting in some other direction, then you have an acceleration in that same direction. But if the force is 0, then there is no acceleration, because that's the only way to make this equation balanced, right? Now what that means, it's very profound, right? You ever heard, probably in popular culture, an object at rest tends to stay at rest. An object in motion tends to stay in motion, right? Those are part of Newton's laws. We're going to talk about Newton's laws of motion. Newton's laws basically says, if I go out in space and I take a ball, and I'm far away from any planets, no forces, and I take that ball and I throw it, and it has some initial velocity. What velocity will we label it? V0. That's initial velocity that we use to launch something from our hands, right? There's no forces acting on it. No gravity, no electric force. We're far away from anything. We're not near anything. There's no rocket thrusters, no light, no nothing. Absolute empty space. Then there is absolutely no force acting on this object, and therefore there must be absolutely no acceleration. That means no speeding up, no slowing down, and no changing directions, because changing directions also counts as an acceleration too. So that means that if I go in space and I throw it, then that ball is going to go in that direction forever at the same velocity that it left my hand from, and it will never change directions, and it will never speed up, and it will never slow down. Why? Because there's no forces. So this equation basically says forces cause acceleration. And kind of as a result of that is, if there's no forces, then things just tend to go in a straight line motion forever. Or if they're at rest, then they stay at rest forever. Either they stay at rest and they never move, or they're going and going and going and they never change their state of motion, their velocity. Remember what we talked about a minute ago? We said the acceleration of something is the change in velocity, how the velocity changes with respect to time. That is what an acceleration is. But if the acceleration were 0, because there's no forces, then that means there's no change in the velocity at all. That means it can't speed up, it can't slow down, and it can't change directions, because all of these are vectors. So if they change directions, they've changed, because a velocity pointed this way is different than a velocity pointed this way. So if it changes direction, it has to have some acceleration, its direction of motion. There has to be some force pushing it. All this means is that things tend to move in straight lines, and thus they're acted upon by some kind of outside force. Or if they're initially at rest, they stay at rest forever, which is what you expect. You put a rock on the ground, it's going to stay there. The only reason it's going to move is if the wind blows it, or someone kicks it, or an earthquake shakes it and it rolls. It's never going to move. And you don't have to put energy into it to make it stay there. Things naturally want to stay there. But once you launch them in motion, they're going to go in the same straight line motion forever, unless acted upon by an outside force. But remember, when we throw things on Earth, they go up like this and they come down. Why is it changing path? It's because there's a force of gravity acting on this the whole way. And we said in our equations down here that g, the acceleration of gravity, was in our equation right here. So forces and acceleration are kind of like cousins. They're basically the same thing, we're just relabeled, because force is equal to mass times acceleration. In the equation of motion we had g, the acceleration of gravity. That's oriented down. We already know forces are also oriented down. So we already know that the force of gravity is in the same direction as the acceleration due to gravity, g. right? And we know that the only reason this thing is curving in its path is because of the force pulling on the thing. If there was no force or no acceleration, there, it would just sail, it would just go forever in a straight line, right? So I'm harping on that because, humanity has changed their thought process on this a lot over the last couple thousand years. Long time ago, people thought that in order for something to move, you must be constantly causing it to move. If it's traveling in a direction with some velocity, you must continually be causing it, maybe pulling on it to keep it going. But we actually learned later that that's not true at all. Things either want to rest or they want to continue moving at a constant velocity. And they will do that forever. The only thing that happens when you put a force in the thing is you make its velocity change, which we call an acceleration. Forces cause accelerations because this thing must be. This is probably the most, there's an old joke in physics that all you need to know is F equals ma, and you can solve about half of any problem, half of a physics course, because it's so fundamental. F equals ma. We're going to spend many weeks on learning how to solve problems just with that, from boulders rolling down, from pulleys, from things sliding down a ramp. Friction is going to be involved later when we talk about the friction, because friction is a type of a force. And so we can do a demonstration, a little demonstration that seems a little boring, but it's one that I think is very useful to have, right? We've already said that if there's a force involved, it's going to cause an acceleration, and therefore if there's no force, we have no acceleration at all. All right? Newton's law is one of the famous Newton's laws, is for every action, there's an equal and opposite reaction. We're going to talk about this a lot later, right? So let's cause this to happen. Let me take my hand, and I'm going to push on this board. I'm pushing right now. I'm pushing into the board. But the board's not moving. So what's going on here? Well, the board must be pushing back on my hand. And I remember the first time somebody taught me that, I was like, what are you talking about? Like, there's not people living in the board pushing back on you. But you see, there has to be some sort of force, some sort of reaction force pushing back on me. Why? Because the board's not moving, right? I'm pushing, so you would think there'd be an acceleration. However, there's an equal and opposite force on the inside of the atoms of the board pushing back on me. So this is really the net force acting on the board. When we say the net force acting on something, we're saying there's multiple forces. What is the result of all those forces? When we say F equals ma, we're saying, what is the total force, the total vector force acting on the object? And I know that when I push on this thing, there has to be a force coming back. How do I know? Because there's no acceleration. The board is not moving. And because there's no acceleration, there must be no net force. And if there's no net force, and I'm pushing on the thing, then there must be an equal and opposite force coming back. There's a situation here where here's the wall, right? And I basically stand right here, and I push on this thing. What I'm trying to tell you is because the wall doesn't move, it doesn't have any acceleration, so the net force has to be 0 on the wall. The only way there could be a net force is if there's an equal and opposite force pushing back. As I'm pushing on the wall, there has to be a force pushing back, because they have to balance to make the net force 0, because this wall is not moving, right? Where's the force coming from? Where is the hidden force coming from? Well, it comes from elasticity. Take a rubber band, right? I can pull on it, it's going to pull back. If you take a piece of matter like this, if I really try to break it, I feel the resistance. Where is it coming from? The atoms are providing a counterforce back. Because of why? The electric forces between the atoms. You see, because the atoms are made of electrons and protons, right? And there's forces there holding them together. There's bonds. You get into chemistry, you talk about chemical bonds, right? They're all in there and they're holding everything together. If I'm trying to pull these things apart, which is what I'm trying to do when I push, I'm trying to break it, I'm trying to pull them apart, but their electric force is incredibly strong, remember? How strong? We just said it is millions and millions and millions of times stronger than gravity. So I can push, but as long as the thing has some strength to it, I can get a counter push because of the electric forces, the elasticity inside of the atoms of the tree or whatever it is I'm trying to bend. That's where the force comes from. So when I push on the wall, there has to be a counterforce, because for every action there's an equal and opposite reaction. Where does it come from? It comes from the elastic forces of the atoms inside the board, and as soon as I pull them this way, they're trying to spring back like a little spring all the millions and trillions of atoms there, to provide a net force. Here's a force, here's a counterforce. The total force, the sum of these forces is 0, which has to be 0 because this board is not accelerating. It doesn't move. Now, if I increase the force and increase the force, and I put a machine behind it, increase, eventually I will be able to push harder than this thing can resist me. What will happen? The wall will break and an acceleration will happen because the counterforce is no longer strong enough to counteract what I'm doing. So then the thing breaks and things start moving. That's an acceleration there. All right, a lot of talking. I guess I get excited about this because, when someone told me in high school, I think, that there was a pushback here, and they told me that the net force acting on this wall is equal to 0 because there has to be some invisible force pushing back, I just didn't believe it for a while. I was like, where? There's nobody back there pushing. But then you realize, wait a minute, no, it's not something pushing back like a person. It's the internal structure of the atoms that are acting like springs. Like literally, if you pull on a spring, it's trying to pull back. If I pull on this rubber band, it's trying to pull back. If I compress something, it's also generally trying to push back on me, unless it's unless it's an object that has no compressibility to it or can be infinitely compressible. But in general, even a gas, if you try to squeeze a gas, it's going to try to resist and push back because the atoms are colliding and increasing the pressure in there. So now we get to talk about one of the central concepts in all of physics, and that is all about energy. So what you start to do after you talk about motion is you talk about energy. Energy is how the universe goes around. Energy is something that we don't totally understand even now, even in modern physics. There's something called dark energy and other things that are, being investigated. We're not talking about dark energy. We're not talking about how galaxies move because there's still some open questions in how the universe works. But certainly we have the basic idea. We have the basic skeleton down. So when we talk about energy, you have to ask yourself, what does energy mean? And there's actually a couple of different flavors of energy we're going to talk about in physics. And the first flavor we're going to talk about is called kinetic energy. Right? And kinetic energy is called the energy of motion. If something is moving at a high rate of speed, we say that it has more energy than if something is moving at a low rate of speed. And if something is not moving at all, it doesn't have any kinetic energy at all. The word kinetic means to move, to have action, to have, to dance, to move. That's what kinetic means. If there's no motion, there's no kinetic energy. And if there's high motion, there's lots and lots of kinetic energy. Now the counterpoint to this, the other kind of energy we're going to talk about in the beginning here is called potential energy. Right? Now, the potential energy is the potential to do what we call work. And we're going to define work later, but work is basically to move something. Your car's engine does work because it can move the car. When I push on a box, I do work on the box because I move the box, right? When something starts here and ends here and it moves, we have done some work on this thing. Gravity does work on this marker because it is pushing this marker and basically pulling it toward the ground. It moves, right? So potential energy is the potential to do work, to move something, right? This is the best example I can come up with. This is a rubber band, right? When it's relaxed like this, there's no potential energy here because there's no potential for this thing to do anything, right? But if I stretch it and now it's in tension, it has a high amount of potential energy because it has the potential to do something useful, like move something, right? In fact, if I kind of let it go, then it hits me and it takes that potential energy that it had and it converts it to kinetic energy of motion. So this is one of the easiest way to visualize the difference between these things here. When I'm in this state, I have a very high potential energy. When I am in this state, I have a very low, basically 0 potential energy. But when I'm in this state, I have also a very low 0 kinetic energy, but as soon as I let it go, the potential energy I had is 100% converted to kinetic energy because the rubber band moved at a high rate of speed. And then, of course, it slammed into my hand and the energy got transferred to my hand. Life is all about energy transfer. The universe is all about energy transfer. physics is basically all about energy transfer. We're going to learn about lots of different kinds of energy. In a big picture, there's the kinetic energy of motion, there's the potential energy to do something, right? But as we study more, we learn about lots of different situations where we're converting energy. Heat, the transfer of heat is basically converting one kind of energy into another, getting a car to move, getting an airplane to move. Take the energy from the chemical bonds of the fuel. The gas or the fuel that you put into the tank has energy in the bonds, in the chemistry. We break them apart by combustion. The heat that is released, that's a conversion from chemical energy into heat energy, and that expansion is what pushes the airplane or whatever, and that is energy of motion, kinetic energy. So we're converting from one state to another. Now I'm getting a little ahead of myself, so we're going to talk a little more detail about kinetic and potential energy. We've all been to the roller coaster, to the amusement park, right? So let's talk about that situation right here. Let's say we have a roller coaster that goes way up high, and then it goes down, and it goes up a little bit and down, and eventually comes to some kind of rest over here like this. So we have lots of different situations. When the car is at the very top right here, and it's really just barely about to, hasn't really started coming down, but it's just cresting at the top, we say that its potential energy is maximum. Because I was using the example of the rubber band, this is a high potential energy when it's stretched out. But another kind of potential energy is gravitational potential energy. Let me ask you a question. If I hold something for here and I compare it to holding something higher off the ground, which one has higher potential energy, potential to do something? Well, the one that's higher off the ground has more potential. Why? Because if I let it go, it's going to accelerate downward. How? It's going to accelerate according to these laws of how the thing moves downward due to the acceleration of gravity, right? But if I let it go from a higher height, it's going to reach a higher speed when it impacts the ground. So it's going to have more potential energy up here because as it hits the ground, it has more, we're going to quantify it more potential to do work. If you could harness that and turn a generator with it or something, then you would have more electricity, right? The higher something is off the ground, the more potential it has to do work, the more potential energy. So this thing is the highest it's ever going to be on this roller coaster, so it has the very highest potential energy. But at this moment in time, its kinetic energy is equal to 0 because the thing's not moving. It's like at 0 right before it does this. So we have all of our energy in terms of kind of stored into the potential energy bucket, right? Now it comes down and it's right about here. And of course, now it's actually going down. It's racing down like this. Now, what happens next? Well, what happens is the potential energy, did it go down or up? Well, now it's lower, closer to the ground, so the potential energy had to go down. But at the same time that the potential energy went down, the kinetic energy went up. The kinetic energy went up. Why? Because the thing is now traveling very fast, right? And then when you go back to this hill, you trade off some of that kinetic energy back into a little more potential energy right here, but not as high as it was here. And then when you come down here, you're picking up more and more speed until finally you get to the end right here, really fast. I draw a larger arrow right here. Here, the potential energy is what? 0, because now I'm right on top of the ground. I have no more potential to do work anymore, no more potential energy, but the kinetic energy is equal to the maximum, right? And notice what's happening. Throughout this entire thing, there's a conversion between types of energy. When you're at the top of the roller coaster, all of the energy is potential. When you're at the very bottom, all of the energy is kinetic, energy of motion. And in between, it's a constant conversion process. It's like 2 cups of water. Let's say I have 1 cup of water here and an empty cup, but I only have this much water. That's all I've got. And I can slosh it back and forth, but I only have 1 cup of water. I can put half of it here, so now each cup has half of a cup of water, or I can put it all over here, or I can put it all over here. But I only had, in the beginning, a 1 cup of water. I can just change the form or where the water is stored, sort of. Here, I only have however many, we're going to talk about the unit of energy later, however many joules of energy I have, that's the total. But it's all stored in potential energy. As it comes down, the potential energy goes down, and the kinetic energy increases at exactly the same rate. When I get down here, the potential energy bleeds all the way to 0, and the kinetic energy is at a maximum. But what we say is, the total energy, which is equal to the potential energy plus the kinetic energy is a constant. It doesn't change. This is called the law of conservation of energy. The total energy of the system, the total energy. When you look at all the different types of energy you have, the total amount of energy contained in this roller coaster system when the thing is at the top, it's unchanged. As the thing goes down to the bottom, the form of the energy changes, but the total energy is the same because you have the same number of joules. It's all in the kinetic energy bucket down here, where it was all in the potential energy bucket up here. All of the potential to do work has bled off, and now there's no potential anymore, but I am going very fast there. So energy can only change forms. This is the conservation of energy. And of course, in real life, we have other things. We have friction in the tracks. That's going to be rubbing, and that friction is going to take some of the energy away from the motion. We have the wind, and we're hitting the wind. Some of the energy gets transferred to the air surrounding the car, and so on. But all of the energy is going somewhere. It's all able to be book kept and tracked. And so in physics, we study where the energy goes to study how the system will behave. All right. After we talk about kinetic energy, we talk about collisions. Right? How do things collide? Because now we know about the law of conservation of energy. We talk about also something called momentum. So when we have collisions here, it means we might have two balls, right? One of them is going this way, and one of them is going this way. And this ball might have V1, and this ball we might have some velocity V2, and this ball is traveling at some angle theta1, and this ball is traveling at some angle over here, theta 2. And the question is, what's going to happen after they hit each other? Because this ball is going to continue in this direction, and this one's going to continue in this direction. They're going to hit each other right there. Now that we know that the kinetic energy, or the energy of the system doesn't change, that's called conservation of energy. We also learn about conservation of momentum we talk about later. We can predict where these things are going to go. What's going to happen after collision? You can think about colliding cars. You can think about colliding particles in a particle collider. What's going to happen? This is all being able to be calculated now that we have the tools of energy to talk about it. All right. The next thing we need to talk about is extremely important in physics, and that's called gravity. Gravity. Whoops, not gravitex. Gravity. Right? Now, the gravity is basically when two things attract. When two objects that have mass attract each other. Gravity, as far as we know, is only attractive. See, the electric force is much, much, much stronger, but it can either repel or attract. Gravity is only attractive. It's only an attractive force. That's, of course, our current modern theories of gravity. Who knows what will be discovered or predicted in the future. Right now, we believe gravity is only attractive, okay? And the situation we have with gravity is, for instance, if we have Earth, right here, and we call this Earth, and we have something over here called the Moon, right? And there is some distance between them, but the distance I'm going to call is r. You could call the distance d if you want to. It's the same thing. Well, it turns out that the force of attraction between these guys is equal to the gravitational constant, which we'll learn later, called g, times the mass of the first object times the mass of the second object divided by r, but not just r squared, right? So if you know the mass of the Earth, and you know the mass of the Moon, and you know how far apart they are, then you can calculate how many newtons of force are acting, or basically pulling those things together. And it turns out that everything in the universe is attracting every other piece of matter in the universe. The farther away you are, the less the force is. In fact, you can kind of see this if we increase the mass of mass 1. If we increase mass 1, then the force increases. If we increase the mass of the Earth, for instance, then the force between them goes up. If we increase the mass of the Moon, mass number 2 over here, then we see that the force, again, goes up because mass 1 times mass 2, they're in the top. You increase either one, the force goes up. But if you increase the distance between them, then the force goes down fast. Right? Because if I increase the distance, remember I'm dividing by a bigger number, then the force is going to go down. But I'm not just dividing by r, I'm dividing by r squared. So if I increase the distance by 100 meters, then it's 100 meters squared. The bigger number is what you divide by. So the force falls off very, very fast from as you get things farther apart. That's why technically I am attracting the star Alpha Centauri, but because it's so far away, the force of attraction is very, very, very small, right? Now you have forces acting on objects, planetary objects. What do we want to learn about next? Typically, we talk about orbits. We talk about the fact that the planets, orbit the stars and things like this, right? So what we can say is that forces and planets, very, very important stuff, and actually very confusing to a lot of people, including me, the first time I learned it. So here's Earth. Let's talk about what an orbit is. Let's say I had a mountain this tall, and I know I drew it weird, but I'm doing that on purpose. The mountain sticks up above the planet, okay? And then what I do is I launch horizontally. I launch horizontally from this a bullet or let's say I throw a rock, and I throw it this way, like this. And what happens is, because I threw it with a very small amount of force, then what ends up happening is eventually it hits the ground somewhere over there. Now, I'm going to do the experiment again, except I'm going to throw it a little bit faster. That's why the arrow is longer. And because I threw it faster, again, horizontally, what's going to happen is gravity is still going to pull it down, but I'm going to make it halfway around the planet before gravity, because gravity is pulling it down at all points on the path, and eventually it pulls it there, pulls it down. But what happens if I do this experiment again and I throw it very, very fast? Then eventually I'm going to hit this point where gravity is pulling it down, but what's happening is it can get all the way back around the planet before gravity can actually pull it to the ground. So people think in orbit that there's no gravity in space, but that's not true at all. There's gravity because the Earth is right there. It's only a couple hundred miles below a spacecraft. It's always pulling on it, but the thing is, you have to go sideways, horizontally, extremely fast in order to go around the planet before the force of gravity sucks you in and you hit the ground. And this speed it comes from the laws of physics. We calculate the escape velocity needed for a spacecraft to make it all the way around the planet. That's called orbit. If you give it even more and more and more speed, the orbit will get bigger and bigger. And if you give it too much speed, it'll escape the orbit, the vicinity of the planet altogether and sail off somewhere else in the solar system. Okay. Another way of looking at this would be the situation of, let's say we have the Earth here in the middle, this E, that's Earth, right? And then we have basically some spacecraft right here. And we're going to say this thing is in orbit. So I'm going to try to draw a circle, but it's probably not going to be exactly perfect. You get the idea. So what's happening here is gravity is pulling this thing in. It is trying to pull it directly toward the center of the planet. However, at the same time that gravity is doing that thing, there's a force of gravity there, the ship is traveling this way at some very high velocity. So yes, it tries to get pulled in, but because it's going so fast this way because remember, if there's no forces, things want to go in a straight line. So if you could just somehow snuff out the Earth and just make it disappear, this thing is going very fast. It would go forever in this direction. But the force of gravity is curving the path, and so it can't go on in a straight line. It curves its path to the next point right here, let's say. Now again, at this point, gravity is pulling in with exactly the same force, but again, the thing is moving sideways so fast that it wants to go in a straight line this way. If you cut the Earth out of the picture, it goes this way, but the force of gravity, again, is trying to change the path. So eventually, instead of going straight, it ends up over here. And at this point, gravity is again trying to pull it in, but again, the horizontal velocity is continually doing this thing, this velocity where it's going around and around. And so it goes around and around and around. We call this the orbit of a spacecraft around the planet Earth. It's not that gravity's not there. If gravity wasn't there, the spacecraft would just go. It would be gone, right? Because we said F equals ma, force equals mass times acceleration. So there is a force of gravity, so there must be an acceleration. But I'm telling you that the velocity is not changing. It's going the same speed all the way around. So where is the acceleration happening? Remember what the definition of acceleration was. Acceleration, from the very beginning, change in velocity with respect to time. But then you might say, well, wait a minute, you're not changing velocity. It's still going the same speed all the way around. But you see, this is the difference in a vector. Because to get a change in velocity when velocity is a vector, you can either get it by changing the speed. We're not doing that here. But you can also change the velocity when its direction changes. You see, a velocity is a magnitude and a direction. And if you speed up or slow down, of course, that's acceleration. But if you also change its direction, there is an acceleration there too, because the velocity vector here is pointed totally different than here. This thing has changed. There is a change in velocity. It's pointed in a different direction all the time. So not only is there a force going in here, but there's actually an acceleration pointed to the center of this situation. And the acceleration is pointed in the same direction as the force. There's a force of gravity and there's also an acceleration pointed to the center. This is called centripetal acceleration. We're going to talk about it a lot later and we're going to calculate it. Notice the force is in the same direction as the acceleration on all of these cases, which is exactly what this vector equation tells us. The force and the acceleration are in the same direction because forces cause acceleration. The force of gravity is what's causing the acceleration, which is causing the change in the path of this satellite, which is what an orbit is. All right, let's move along. The next thing we typically learn about in physics is we talk about gases and fluids and things like that, gases and fluids. Right? So a long time ago, people thought that when something had heat, that heat was like a substance that you could just pour it from one thing to another, right? They had words for it. I don't want to get into the history too much, but people really thought that heat was something that was a fluid. It was like a fluid that flowed between hot to cold, for instance. And it took a long, long time for people to figure out that heat was nothing more than the motion of the atoms inside of an object. So if I have a can, let's say, and it's got some gas inside, right? So I have a particle right here, it's moving this direction, particle right here, moving this direction, particle here, this direction, particle here, that direction. So what's happening is these atoms of gas in the can, they're hitting the walls, they're bouncing off, they're hitting each other, they're bouncing, they're bouncing, they're bouncing. And the temperature of the object is directly related to how fast those atoms in the can are moving. And of course, the more collisions that are happening, the more pressure inside of the can. That's why when you heat something up, you shouldn't heat something up inside of the can because the pressure can get high and the thing might explode. In the past, people thought heat was like something it was like a fluid that was like a separate thing, a separate quality of a substance. But now we know that the heat of an object is just the thermal motion of the atoms there. And so now that we know that, we can use all of these ideas of motion, all of this energy and motion and all the stuff that we learn in physics can be applied to heat. And that whole topic is called thermodynamics. Thermo means heat, dynamics means to change or to move. So we can build engines, we can calculate how efficient an engine is, and so on, based on these ideas. All right, after we talk about gases and fluids, we talk about waves. Now, waves are important because we're going to get to electromagnetic waves very soon, right? So what we have is a situation where we have a wave which can travel. Let's talk about waves on a string, right? Which has a wave speed, we call it v. A wave is a disturbance that propagates with some speed and also some frequency and some wavelength, which is how wide the wave basically is. And so we learn about how to calculate the speed and the wavelength of the wave. The wavelength is basically the distance when the wave starts over again, for instance, right? And we also talk about the situation of what happens if we have two waves that can basically collide with each other. So instead of a wave going this way, we have two waves, one going this way and one going this way. What's going to happen in this situation, or what could happen in this situation, is these waves can add together. So if two waves are coming in opposite directions like this, what you can have is a situation where the two waves basically add together. You can have a situation where it gets very, very big. The crest and the trough kind of add up together because the tippy tops here line up and they add together, and the troughs line up and they add together like this. But you can also have a situation where they subtract from each other as well. So let's take a look at that situation. So this situation, when they add up together, this is called constructive interference. Right? Constructive interference. But then we can have a situation where we have destructive interference as well. We can have a situation where we have a wave that goes something like this, right? And then over here, if a wave comes in the other way, this one can go this direction and this one can go this direction. Notice that these waves are flipped around, like the crest up here is the trough. They're basically reversed from each other. And you can have a situation because of that happening, that what happens over here is when they add together, they basically subtract, because the crest here adds up with the trough over here to make 0, and the trough here adds with the crest to make 0, so this is called destructive. It turns out that the interference of waves is very, very important for studying lots of things in modern physics. We're going to talk about waves a lot, but basically all the modern theories of physics and how matter works and all that stuff, they're all wave theories. So the ideas that we learn about how waves can add or subtract here, they apply to sound waves and other things, but they also apply to, like I said, matter wave. We have matter waves and energy waves and things like this in the future that we learn about when we get to quantum mechanics. Quantum mechanics is a wave theory of matter. All right, so I'm going to pause here. We'll pick it up and we'll resume the rest of the introduction to physics. Learn anything at mathandscience.com.